Okay, welcome to this last and final lecture of the computational thinking course. What I want to do is quickly summarize all the concepts that we have learnt so far that have been introduced in the course. So as you go through these slides, and I hope to finish these slides reasonably quickly, you will see certain words highlighted, which means shown in dark, bold. Those are the keywords. Those are the, in some sense, glossaries, right? Think about it like the glossary of a book. Those are the words, those are the concepts that we have introduced in the course. So you want a quick summary of just the words. By words you want to remember the course, and the ones that are marked in bold are the ones that you should keep a watch on. Okay. So we started this course by asking what is computational thinking. So we said computational thinking basically is trying to express a solution to a problem as a sequence of steps so that we can communicate these steps to a computer. That's basically the objective, right? And then we said, let's try and see whether we can write these steps in a way that basically allows us to identify, to write it in a correct way, you can identify patterns between different solutions. And then looking at these patterns, you can create code which basically can then be reused across multiple applications. That is basically, if I have a new problem, completely new problem, then I can say, this problem looks very much like that other problem that I saw. So can I simply take the code from there and use it? And that basically is enabled by computation, right? That is the idea. Now, specifically in this program, we are looking at data science, right? We're not just thinking generally about computation thinking, we're thinking about computation thinking in the context of data science. So, in data science, the problems are usually posed on data sets that are available, right? So, you have a data set, you ask some questions about it. Now, these data sets can come from real life artifacts. As we saw in this course, we had basically a number of real life artifacts like shopping bills, we had the train timetable, we had classroom data, we had words and so on. But in principle, you could also have transaction logs, you could have many things like that. You could have, emails, you could have, chats, all these kind of things. These are all basically various kinds of real life artifacts you can analyze to do a lot of things. Or your data might actually be processed and available in a digital format, like in the form of a table. So it may be stored in an Excel sheet or some other sheet, and you may have it in the form of table, right? So you can use the table data also to process. So we have tried in this course to accommodate both by using cards to give you a feel of how you do things with real life data, and through tables and rows on the table and so on, you get an idea of how to do things with digital data, right? Now, in data science, computational thinking involves finding patterns in methods used to process data. There are generic patterns. In fact, actually, there are many interesting computational patterns, but we didn't discuss many of them in this course, right? So, don't think that this is a course on all of computation. It's not. It's just a peek into the world of computational thinking, wearing the lens of data science, right? So, you are basically entering data science and looking at it from a lens, from looking at the computational aspects of data science in some sense. So, we have introduced a number of concepts and methods that would help you hopefully when you finish your 3 years of whatever it is that you do in this program, you will probably come out with a very good idea of how to process data sets that come out from various places, and when doing that, what kind of thinking you need to have in terms of computationally processing them. So we saw that basically there are some elementary steps. The first step basically is to take this data set, scan it, right? And we saw that iterator is the way to scan it. We'll come to it, right? So you scan the data set and collect relevant information. The second is process it, which means that you may make a list, a dictionary, something like that, and or a graph or something. Finally, you want to put all this together in some neat way. For example, you write some procedures, make an object, make it concurrent, all those kinds of things. So first, scan for relevant information. Next is process to make relationships. And third, basically, is to organize. These are the things that we learned in the course as various things. Now, the most powerful construct that we saw that can be used to scan or process intermediate information is the iterator. Right? The iterator is basically something that needs to be initialized, and you have to say what is it that it's iterating over, which is what is the repeat step, what is it repeating again and again, and most importantly, you should know how to exit. Right? We saw that it's not that easy to figure out how to exit. Sometimes you can write the exit by writing the while condition carefully, by adding more things to the condition and the exit. Sometimes in the middle of the iterator, you can put an exit loop and you come out. Okay, that also is possible. So you should know how to exit from an iteration. Not only that, when you exit from the iteration, where should you go next? You should know that, right? So that is the other thing that is important to know. Now, while iterating, you may have to hold values, and we said basically variables are the storage units that are used to hold values. that are used, they are computed, produced during the iteration, right? You are iterating over the data set, like a bunch of cards, rows of a table, or a list, elements of a list or something like that. And while you are doing that, you are keeping track of something, and that keeping track is done using variables. Now, you have to initialize the variables, and then you have to update the variables. Both the initialization and update operations are done using what are called assignment statements, right? And when you have certain kinds of variables which are just accumulating something, like it's accumulating the sum of something, total of something, or it is basically accumulating a list, making a list, these variables are called accumulators. And accumulation operations look very similar in various cases, which is why you want to separate them out as a pattern, right? Accumulator pattern. We saw two kinds of ways to write this. One is a flowchart. We didn't talk much about flowchart after some time because after some time drawing these kind of diagrams is very hard. But we saw that a flowchart is useful still to depict as a pictorially, right? When it's a small thing, it's always good to write the flowchart. Easier to see it. So we saw basically that there's these symbols which are called the terminal symbols. Start and end are terminal symbols. Terminals. Then we saw the square boxes, which are these processes or activities, activity or process. And then there is this decision box, right? This is diamond, right? So you can have diamonds which are basically decision boxes, and then you can connect the boxes using these arrows, and that's how you make flowcharts. And the same thing can be also written in pseudocode. So the pseudocode, the most important thing we saw was the while loop. The while loop basically allows you to do iteration. So while file 1 has more cards, do something, right? So this is an iterator. This pattern over here, which you saw in the flowchart, this loop in the flowchart basically is an iterator. So this is an iterator pattern in the flowchart, and this is an iterator pattern in the pseudocode. Okay. Now we also saw basically that the items that we are collecting, these variables, the data that we are processing and collecting, the variables, can have different data types. The basic types, basically I talked about were Boolean integer character, and then we had this interesting type called string, right? String of characters. So like a list of characters, but we wanted to separate it out and call it. Then we said that we can make subtypes to put constraints on the range of values. So we don't want to allow negative values, we don't want to allow this, that, and so on. We can put constraints and operations also. You can say this operation is allowed, that is not allowed. Then we said we can make compound types like lists. We can make lists out of things, we can make records out of things. A list is typically a sequence of things with the same data type, and a record is a set of things with different data types. But because they are all different data types, you need to name each thing. In a list, you can identify things by its position, whereas in a record, you cannot identify by its position. You have to identify by a name, right? So you have name fields in record. Now later on, we introduced this new crazy thing called a dictionary, right? List we saw, it's fine, list is okay. We introduced later on a thing called a dictionary. Some of you may be wondering, what is this record, what is this dictionary, are they the same, are they different, and so on. The difference really is that in a record is fixed, right? All the fields are given to you. When the data type is defined, the record is defined. So all the fields are defined, so you can't do anything. Whereas a dictionary, you can keep adding fields, you can delete the fields, you can do all those things. So dictionary is like a record in the sense that you can do x dot a. In a record, you can do x dot a in a dictionary also, or you can do x along with and put in square bracket and put the thing. But dictionary is like a record, but the difference between dictionary and record is that in dictionary you keep adding new fields. Any number of fields you can add to the dictionary. Okay, that is basically it. That's why it also looks very much like a list in some sense. It's random access. It looks like a matrix and all that. So that's why we separated it out and we had a special treatment given for dictionary. It's a very important thing that we will keep using again and again throughout whichever programming language you encounter later on. Then we saw that there is this notion of filtering. Filtering basically means writing a condition which basically can select data elements of the things that we want to process. We want to ignore a number of data elements, only select things that are interesting to us. So you can put a filter, and that filter is returned by using conditions. Now these conditions can be simple conditions, Boolean conditions, they can be compound conditions, and that can be made by using and, or, not, and all some simple conditions. Or you can write conditions one after the other sequentially. You write one condition and do something, you write another condition and do something else. So if something do, then again follow it with another if something, do something. Or even you can nest it. So you can say if A, then open bracket, if B, open bracket, then do something. So you can nest the conditions, you can sequence the conditions. They are not the same, they are sometimes the same, sometimes not the same. You have seen all these examples. Hopefully by now you have figured out all these little tricks that we ask in terms of questions for exams and so on. But you have to understand that these conditions can be written in many ways. Some are equivalent, some are not equivalent, and the programmers may choose to use one of these based on whatever they like to do. Okay, in some sense. Usually, if you can do it in one way, you can do it in another way also. But people have a preference for one way over the other. Okay. Now, the filtering condition can be working on fixed data constants, or it can work on variable. If it is constant, then the filtering condition is not changing with every iteration step. So we saw, for example, accumulation of count and sum and so on. Filtering condition typically does not change. Typically in accumulation, the filtering condition doesn't change. Whereas if you are doing something like max, finding a max or something, your filtering condition is comparing the value with the current variable value max. So that is comparing with the variable. So in this case, basically your iteration, filtering condition keeps changing as you proceed in the iteration. Accumulation with filtering gives you plenty of power. Typically with just iteration and filtering, you can do 90% of the tasks. Okay, most of the things you can do with it. So accumulation with filtering is a powerful concept that allows you to collect all kinds of interesting data and information from your data. Okay. Now, once you have collected, done all these crazy things, you may want to encapsulate whatever code you have developed in terms of procedural parameters so that it can be reused somewhere else. We have seen basically that sometimes it's necessary for us to use the same kind of pattern of code immediately. So if you could write it out, you can separate out the code that you have written in the form of a procedure and give it the right parameters, then that facilitates reuse of the same code many places, right? So we saw examples of this in terms of average for physics, average for maths, average for chemistry, they all look the same. So we can make a procedure out of it. So the procedure can also return a value, and this return value can be assigned to a variable. This is a very, very compact, cute way of writing code, right? Writing x is equal to p of a. Send a to p, get the result and store it in x, all written in one line. Beautiful compact way of writing code. Okay. Then we saw that procedures can have side effects. It can change the values of the parameters. It can change other variables and so on. And when procedures have side effects, you need to manage these procedures extremely carefully, because if you call a procedure and it does something to some other variable which is not even passed through the procedure, then you don't know what's going on, right? Okay. Now, iterations can be not single, they can be multiple. How can they be? How can you create multiple iterations? Two iterations, for example, can be carried out one after the other or one within another, right? And they are different. You know that they are different, right? So you have studied it. By now you have done enough problems to to learn that these are very different things, right? So when you do sequential iteration, that is one after the other, you are processing the one pass is processing the data to create some intermediate information. The second pass is using this intermediate information to do something. So usually you are finding the relationship between an element and the aggregate. For example, you can do first pass to find an average, and the second pass you can find to collect all the students who are above average. So the first pass is basically accumulating the sum and finding the average. Second pass is basically using that average to accumulate a list of students above average. Right? This is what you're doing. So both filtering accumulation only, but you're doing one after the other, and you're using the result of the first and the second. So this is an example of sequential iteration. Whereas in nested iteration, you're trying to find relationship between pairs of elements, right? So whenever you try to find relationship between pairs of elements, you have to nest one iteration within another iteration. And you are doing therefore n square. There are n elements, and you're comparing n elements with n elements. You're doing n square operations, so it's very costly. So you could try and say that I'll not compare everybody with everybody else, I'll try and compare only with those who are relevant to compare. That's called binning, and whenever possible you should do that, because otherwise n square can turn out to be high. Especially with the kind of data sets we learn to deal with, they're going to be large. Like 100,000 data elements, if you try to do n square 100,000 into 100,000 is very, very large. Computer will do it. Okay. So we have to be careful about large data. Then we said basically that we could produce the relationships and store those relationships. How do you store the relationships? Typically in the form of lists, maybe sometimes dictionaries, and then we learned this beautiful thing called graph. Okay. What is a list? A list is just a sequence of values. You can append lists, you can add an element to a list, you can iterate over a list. This is most interesting, right? So we saw that we created, not only did we create this object called list, we created an iterator for the list, for each, which will basically go through the list. Then we had ways of disassembling the list. You can take the list and break it up. How do you break it up? You can find out the first element, the rest of the list, or you can take out the last element and the beginning of the list. So you can take out the beginning of the list and the last element, or first of the list and the last element. So you can break the list up and do things with it. So this is another interesting thing. Okay. Then we said that basically lists which are sorted in ascending or descending order are extremely useful to solve many problems. Okay. How do you sort a list? You can, simplest way is insertion sort. There are many other ways of sort, but we are going to discuss it in a future course, data structures and algorithms course. So this one just introduced one which is called insertion sort, which is simply repeatedly inserting an element at the right place. Right? That's it. Now when you sort the list, then you can do many things. Like for example, if you want to award grades, you just have to take the list, divide it into 4 parts and give the grades. Very, very simple. Okay. If it is sorted, if it is not sorted, it's not possible. So it's easy to do things with the sorted list. Then we saw this thing called a dictionary, which is basically a set of key value pairs. You can insert a key into a dictionary. You can iterate over a dictionary, right? So for each key, this is an iterator. This is the iterator for a dictionary, right? Now, just this one got, I think, I made an editing mistake yesterday and edited it. So, so this is an iterator. I can check whether the dictionary has a key by using this key. And the basic template basically is to check whether the key is in the dictionary or not. If it is in the dictionary, then you can do something. Not in the dictionary, you can do something like, for example, you can create the key, put the key in the dictionary and so on. This is a symbol for an empty dictionary, right? So dictionaries are very, very useful things because it gives you random access. It's much faster than accessing an element in a list. Finding an element in dictionary is much, much faster than finding an element in a list. Okay. Which is why you should use dictionaries wherever it makes sense to use. Sometimes it makes sense to use lists. Now we saw another type of interesting thing called a graph, right? Whenever you have a relationship where you want to show that I is related to J, J is related to K, K is not related to I, you draw edges, right? Between I and J, if I is related to J, J to K, you draw an edge from J to K, K is not related to I, so there is no edge. So the matrix, you can write a matrix, it's called adjacency matrix. Mij. You set it to 1 if there is an edge, you set it to 0 if there is no edge. So when you draw the matrix, full matrix, you write, look at it, the entire graph is captured inside this matrix nicely. It's compact, otherwise you have to draw the graph, it takes a long time, the matrix is much easier to see and do things with. So sometimes you do things with matrices, right? So you can iterate through a matrix to get aggregate information from a graph. For example, you can find out the paths in the graph, which is a sequence of edges. You can basically find longer and longer paths, right? And if you label the edges, you can use it, for example, to find the shortest distance. You can do, right? Then, as a sub-product, as a kind of a byproduct of doing graphs, we basically brought out the idea of matrices, which allows you to access an element I, j randomly. So you can find ij quickly, right? Mij. And there are direct implementations of matrices in many languages, right? Like most languages that you have seen, there is a very strong direct implementation of matrices. You have seen it already. But we have deliberately chosen to introduce matrix only from the perspective of data science in this way. After we have talked about lists and dictionaries, because otherwise we get into the lazy habit of using matrix everything. So we don't want to do that. Okay, so we can implement matrices using nested dictionaries, right? So that allows us to use these iterators for each row in the matrix and for each column in the matrix, right? So we can nest for each row in a matrix followed by for each column matrix, or each column in a matrix followed by each row in a matrix. You can do this nested iteration and process the entire matrix. Okay. Then we moved on to the more advanced concepts in computation theory. First most advanced concept we discussed was recursion, right? Now, why do we need recursion? You can say, hey, I don't need recursion. I am happy with iteration. Iteration is very powerful. Problem is, iteration works on structures which are kind of linear. For a list it makes sense, for a deck of cards it makes sense because it's a deck, right? I can go one after the other. Some structures are not linear, right? So in that case it becomes harder, like a graph. How do I iterate over a graph? Very difficult, right? How do I iterate over a tree? Extremely difficult to do. So for these kinds of structures, it's a more natural thing to do is to use recursion. Now you will find basically that many of these structures, which are graphs and trees and so on, also defined inductively. Which means you say that you make a tree by starting with a leaf node, taking 2 leaf nodes and connecting them into another node. Like that you make a tree. Similarly, a graph is a thing, set of nodes which are connected by edges. We can talk about it later. So recursive procedures basically take functions which are inductively defined or structures which are inductively defined and go through them systematically. How does it go through it systematically? Firstly, it identifies what is the base case. In the case of a tree, for example, the leaf would be a base case. In the case of integer, 0 might be the base case. For a list, an empty list might be the base case, and so on. You have to define exactly what you should do in the base case. If you don't take care of base cases, all the base cases, your recursion may not terminate. Okay, this is very, very important to keep in mind. Don't be lazy when you do recursion. Think about your recursion, think about the base cases, think about what are the possible base cases that will come up in your recursion, and handle all the base cases correctly. Otherwise, your recursion may not terminate. Then comes the inductive case, where basically you take the input and reduce it to a smaller input. The smaller input will eventually become a base case, and then you will address it there. Okay. And then when you find that you have broken it down into smaller inputs, you call the recursion, call the same function for smaller inputs, and you wait for the thing to complete. A simple example that we saw for recursion is depth first search, right? It's a systematic way to explore a graph. You keep track of all the visited vertices in a dictionary, right? So a scene dictionary or something like that, and you can discover all the properties of a graph. For example, you can check whether the graph is connected in a beautiful way using depth first. We then moved on to the second advanced concept, which is encapsulation, where we said it makes sense sometimes to package both the fields and the procedures into one packet, which is called an object, right? And what are the advantages? The advantages basically are that the state is retained between two procedure calls, so we can use that to speed up the procedures. Side effects are made explicit, in fact more natural. Sometimes it's good to have side effects in object-oriented programming. Instead of making it bad in procedures, side effects are bad. In object-oriented programming, side effects are good. Okay. Then we said we can have derived types, which will basically extend the functionality of an object to a more specific extent. We saw in the case of shirts and in the case of grapes and so on. Like the disadvantage with object-oriented programming is that you have to make a lot of objects and initialize them. So that takes time and it's a lot of effort. Okay. So, and also you can try to find patterns which not only involve code but also involves objects and code together, right? We saw that. So that is an interesting thing that we can do in object-oriented computing, find object-oriented patterns. Then we moved on to concurrency. Very hard topic to understand. Hopefully you will keep coming across more and more, and as you absorb more and more of this concurrency thing, you will get to grips with how to deal with this. Basically, it means you are running many things together, and when you do that, a lot of things can go wrong, can go right. But basically, what we are doing is we are taking a remote processor call and unbundling it. Two ways of unbundling it with this, because one is polling and another is producer consumer. In polling, the caller starts the procedures and waits for the procedure to complete. The procedures then basically tell it, the object which is called basically tells it it's complete. When it tells it, the caller retrieves the result. In the producer consumer model, the producer sends a buffer to the consumer, consumer sends a buffer to the producer. Producer, when it finishes, writes the result in the buffer. Meanwhile, the consumer can be doing other things. When the consumer is done, it can read the value from the buffer and move on. This is how producer consumer model works. Okay. In both cases, there are race conditions, and these race conditions can cause corruption of various shared objects like lists and so on. So we have to ensure basically that the shared objects are atomic, right, or non-concurrent. There is no concurrency inside a list. There is concurrency outside the list, right? So you have to make it work. Finally, input-output between a user and a computer, for example, is actually concurrency at work, right? So you have to understand concurrency, you have to understand input-output. Finally, we looked at bottom-up computing, which is a completely different paradigm. The reason why we wanted to touch on bottom-up computing in a computational thinking course is because we see a lot of it in this program, right? As you go forward, you will see more courses which are going to come on machine learning and this and that and so on. And all of them are bottom up, they are not top down, right? And you will of course see there are two streams that you have in this program. One is this programming stream, which will have all top down, and you have this machine learning and kind of things which are all bottom up. You see both streams going on in parallel. So we wanted to give a flavor of what this bottom up computing is. We saw that there are two kinds of problems: the classification problem, where you try to label every element by using a decision tree, and a prediction problem, where you try to make a numerical function which can predict the value of an unknown value from a known value. Right? Both of them can be combined. You can make a decision tree where the branches are taken based on prediction function. You can make a decision tree and the leaves of it can be prediction. So that is also possible. Right? Both can be combined. That we come to the end of the computational thinking course. I hope you enjoyed all these lectures and material that we put out for you. Madhavan and I we can share with you that we really enjoyed putting all this content together and seeing all your comments and interactions and so on. We have enjoyed it, and I hope you enjoyed it as much as we did. wishing you all the very best for your exams, and more importantly for the rest of this program, which is going to be, I bet, much more exciting than what we've done in computer science. It's going to get more and more exciting as we go along. All the best.